Okay, continuing on then, we need to talk about the difference between having balanced and unbalanced forces. So the first law of motion comes into play when all of your forces are balanced. So if you think back to when I talked about, two people pushing on opposite sides of a table, if they push with the same amount of force, then they really balance each other out, right? You end up with no net force. If you have a force of like 3 newtons to the right and 3 newtons to the left, well, all in all, that arrow, add up. Remember how to vector add, right? That'll add up to 0. And so you have 0 net force at that point, no acceleration. But does that necessarily mean you have no velocity? Well, I hope the example of the skydiver proves to you that even though you have no net force, you can still continue to fall, right? It's not like magically terminal velocity means you don't die without a parachute if you jump out of an airplane, right? You will hit that terminal velocity, but you'll just continue to fall at that same velocity, right? And the same is true of anything. Like if you're pulling something along the ground and you pull with a certain amount of force, right, and friction is acting with a certain amount of force, and those happen to be equal, well, then the thing will just continue to go at the same speed, right? But we do call that equilibrium even though it's still moving, right? Even though the skydiver is still falling, even though the object you're pulling is still going across the ground, we do call that an equilibrium because there's an equal amount of force on all sides of that object. Okay, so first law of motion is also called equilibrium. It's also called the inertial law. Okay. Now, what about when forces are not balanced, right? Let's say I had 2 people pushing on the same thing. One of them is pushing with 5 newtons and one's pushing maybe with 2 newtons, right? Well, in such a case, now you have unbalanced forces, right? If you were to add those arrows up, they wouldn't add up to 0. And so you will have a net force of something, right? And if you have a net force, then we're going to have to use what we call the second law of motion. Now, the second law of motion says acceleration is going to happen, and that acceleration is going to be dependent on 2 things. It's going to be dependent on the force applied, or the net force applied, I should say, and it will also be dependent on the mass of the object. Okay? All right. So here's Newton's second law. Formally, it says when a net external force acts on an object with mass m, all right, the net force is equal to the mass times the resulting acceleration. Now that's a fancy way of saying that the more mass something has, the less acceleration it will have generally, right? Because if it's 2-ton rock and you push on it with a lot of force, it's not going to go very far. But if it's a pebble, right, a 5-ounce pebble or something, and you push on it, well, it's going to go flying, right? So mass is inversely proportional to acceleration, right? The more mass, the less acceleration. You can also say that the more force, the more acceleration, right? So if I increase the force, I increase the acceleration. By the way, this little fancy symbol, if you haven't seen it before, that is the sum, right? It means the sum of, so it's the sum of the forces, or the net force, or the total of all the forces, right? When you add them all up. And again, sometimes they're going to be positive, sometimes they're going to be in opposite directions, so you'll consider them negative. Like the example of the 3 newtons to the right and 3 newtons to the left. Okay. One other thing you could say also is that the second law of motion also kind of includes the first law of motion in it, right? Because if you have no net force, if your net force equals 0, then your acceleration has to equal 0 as well, right? You might see that in this equation, right? So first law is the special case where F is equal to 0, the net force is equal to 0. Okay. All right. Now, the units for force are the Newton, which is really, if you look at this equation, it makes a lot of sense. We have kilograms, right, for mass, and we have acceleration, which is meters per second squared. So if you just combine those, kilograms times meters per second squared, That's how you get the Newton. Okay. And of course, named after Isaac. Here are your typical forces that you'll be looking for in a problem. We do have the non-contact forces sometimes coming into play, especially gravity early on. Later on down the line, we'll talk about electric and magnetic. But then we have our contact forces that you'll tend to see. When you just push on something, we call that applied force. So this is like a push, or it could be a pull. Doesn't matter. We have springs. You might use springs in certain situations. Air resistance we've talked about, like when you were jumping out of the airplane, right? Normal force is a special one. This is the one that surfaces give when you push against them. So, for instance, if you put your hand on the table is going to push back up on your hand with a certain amount of force, right? Otherwise, your hand would go flying through the table. And so we call that the normal force. Tension would be anytime you have like a rope or a string that you're pulling with. Tension would be involved in that. And friction, of course, is when you try to move something across a surface. When you go across the surface, right? Friction is what slows you down. It's the slowing force as you have motion across a place or a surface. Okay? So those are your typical ones. Yes, there's some other instances about there, but those are the ones that you're mostly going to see. Now, when we go to write these forces in a way that is sort of useful for us pictorially, right? We write what we call free body diagrams, or we draw free body diagrams. And we do this with arrows, right? We're going to do this with arrows. And you're either going to do one of two things with all of these. You're either going to draw a box for the body that is being acted upon by the forces, the object, or you're going to draw just a big dot. I don't care either way. Either one is fine. I learned back in the day a box. Nowadays, they often use just a dot. It really doesn't matter, right? But you'll draw arrows from this. So you'll draw like a force arrow up for a force that's going in that direction, right? You'll draw a force arrow to the right if it's going in that direction, or, something like this, okay? All right. So here are a few example free body diagrams. And I just want to talk about these for just a minute and then give you a chance to do a few of your own. Okay. So in the first picture I have here, this is what we would call a very balanced situation, right? This is a very balanced situation. I have a 5 Newton force to the left, a 5 Newton force to the right, 3 Newtons up, 3 Newtons down, right? And so if I was to add all those arrows up, they would add up to, of course, 0, right? So the net force, in this case equals 0. So you could say that about it. One other thing you can say about this is that this would be a situation where I have a push, right? The applied force is going to the right. I have a push on something that is